Hello again, beautiful physics kids. We're going to be talking about kinetic energy and potential energy right now. And you probably learned a little bit about these two things. Potential energy is the energy of position. Now we have gravitational potential energy. Lift your calculator up, drop it. Oh, it would release energy if I let it hit the ground. Gravitational potential energy, then. I have worked against the force of gravity and lifted something up. Well, it turns out any of those magical forces we talked about, if you work against them, you store potential energy. If you take two electrons, they don't want to be close together. If you push them close together, well, you've stored potential energy. This would be electrical potential energy, also known as voltage, right? Electrical potential energy. If you look at the sun, that's nuclear potential energy happening because of the strong force pulling particles together in the center of the sun. So potential energy covers a wide range of understandings. We're just going to be working with mechanical ideas of potential energy, and then we'll extend that later on to some of the other forms of potential energy. So potential energy, we take an object. Oh, okay. When I was a little kid, I remember they used to have, in my grandparents' hotel, they used to have these really big cans of vegetables and things like that. But, I mean, you're making food for hundreds of people. They're called number 10 cans, and they're really big cans. We would put them up on the high shelves. One time we had filled the shelves a little too full on the high shelves, and everybody's busy underneath them, and somebody bangs a wall or something, and one of the cans from up on that high shelf falls off, hits my cousin on the foot, and breaks his toe. That can had a lot of energy stored in it. You can imagine, and if you were in class, I'd goof on you this way. I'd take this 1 kilogram mass and I'd put it on your hand and I'd say, is that okay? Yeah, so the 1 kilogram mass sitting on your hand, not a problem, right? 1 kilogram mass sitting on your hand, not a problem. But what if I lift it up here and drop it? Problem. Okay, I've stored energy in it. So when it gets back down to your hand, it still has that stored energy. That could hurt your hand and imperil my job. So when you store energy in it by working against the gravitational field, that energy then can come out when you release it and be released as it comes down. But we got to think about it. When it gets back down here, after it's fallen, isn't it at the same position? So isn't its potential energy zero? Well, it is. When it gets back down to the ground, its potential energy is zero. So what form is it carrying its energy in? You'll recognize it's carrying its energy in the energy of movement, and that is called kinetic energy. So we have two different formulas to handle each, but we have the bigger understanding of potential energy getting converted to kinetic energy on the way down. We also tell the story of Midway, and if you've seen the movie, I don't think they bring it out so well, but essentially there were groups of pilots that were attacking the Japanese carriers in the Battle of Midway, and these very, very brave people flying these airplanes, their fighter escort didn't show up. They were in their dive bombers, and they decided to attack anyway. A very brave decision, because there's these Japanese fighter planes all circled around, and these Japanese fighters can outmaneuver them every which way but loose. And so the torpedo bombers dive, and the Zeros, the Japanese airplanes, dive after them and shoot them all up and wipe these poor people out. They gave their lives. But now, the fighter planes, the Japanese fighter planes, were on the deck, were down low. How long does it take to get up high again? Well, you can only put out so much energy, which means you can only climb, you can only increase your potential energy so fast, so it takes them a long time to climb back up again. Meanwhile, a whole other wave of American bombers have come in, and the Japanese airplanes are down low. So that allowed the attack to continue. And if you study history, Midway was a complete turning point in the war. And it all has to do with potential and kinetic energies. If you're in an airplane and you dive, you're turning potential energy into kinetic energy by diving. And if you're in an airplane and you're moving too fast, all you have to do is pull back on the stick and climb. Now you're turning kinetic energy back into potential energy. You're rising up, right? So the energies go back and forth. Heck, if we see a pendulum, pendulum is kind of cute because as the pendulum swings back and forth, when it's at its lowest point, I'll draw it for you. When the pendulum is at its lowest point, what does it have? Does it have any potential energy? Let's take a look. At the higher points, swings over here. Swings over here. All right, and you can tell these are up higher than this. So these have potential energy. So as the pendulum swings, we have PE. When it gets here, it's moving fast. It's all been converted to KE, and it swings up here, and it's back to PE again. And so a swinging pendulum constantly converting energy from potential energy to kinetic energy. So let's look at the equations, shall we? Potential energy, well, you have a force pushing downward. We measure in newtons. This would be 9.8 newtons. Talked about that earlier. 9.8 newtons pushing down. If I push it up 1 meter, all right, well, let's see. The potential energy formula all right? Well, it's how much force you're putting on. And force, we know, is mass times gravity. 1 kilogram times the 9.8 meters per second squared in our gravitational field here. Mass times gravity. And then pushing it, how high up did you push it? So very simply, the potential energy formula is mgh. Let's just take a quick look at the units. Kilogram meters per second squared times meters gives us kilogram meters squared per second squared. What unit is that? That's a joule. Okay, that's the unit of work and energy, a joule. Okay? Kinetic energy now. This one do pay attention to because this really, really matters when you're driving. This formula is sad. Why? Because humans don't get it. You can learn this formula, but unless you internalize it, the formula won't save your life. But if you internalize this formula just a little bit, it very honestly might save your life. I know that because I've had way too many good friends of mine perish because of this formula. Check it out. Kinetic energy is 1/2 mass, not times velocity, times the square of the velocity. That's the problem. If you're going twice as fast in your car, the kinetic energy you have is not twice as much, even though your gut will tell you, yes, it seems like it's twice as much energy. It's not. Because it turns out, of course, that kinetic energy is proportional to the square of the velocity. The square of the velocity. So if you're going twice as fast, you have 4 times as much kinetic energy. 3 times as fast, you have 9 times as much kinetic energy. This can be devastating. So a car can only handle so much. That 5-mile-an-hour difference, where you reduce your speed just a little bit, can make an enormous difference if anything goes wrong. So be aware of that. Our brains do not tell us that. You need to take physics to really learn that. So here's the 2 formulas. But this is the greater understanding. Take an object, drop it. Okay? We're not going to put numbers in here, but up here, it's not moving. What does the object have? It has potential energy equals, I will just call it X number of joules. Oh, heck, let's put a number in. Let's call it a nice easy number. 100 joules of energy. Okay, 100 joules of energy. when it gets down to the bottom, well, it's down to the bottom now. Height has gone to 0, so you know potential energy has gone to 0. Okay, so if PE equals 0 joules, where are the joules? Did we have a joule heist here? No. Turns out the kinetic energy equals now 100 joules. What was the kinetic energy up here? What wasn't moving? So that's 0 joules. So in other words, the energy total as this object falls stays the same all the time. It had a certain amount of energy in it. That energy stays in it. What's the energy at the halfway point? Right? If you use the kinetic energy formula to figure this out, you got to do a fair bit of calculation. You certainly can. It's not hard. How fast is the object falling after a certain distance? That's what we learned months ago. That's easy. But what's more important in what we've learned is how to approach a problem. Why do we take a harder route, even though it's not all that hard, when there's such a simple understanding right in front of us? Potential energy is mgh. So potential energy is proportional to the height. So if I've cut the height in half, what happened to the potential energy? Excellent. So the PE here would equal half, or 50 joules. You know you're not doing any joule heists here. So where's the rest of it? At the halfway point, the kinetic energy must also equal 50 joules. Okay, not so bad. Actually solving the problems, Given's formula S and S, is really not so bad either. You recognize by this time in physics, you've been solving problems, Given's formula S and S, the same way for so long, bells notwithstanding, you've been solving them for so long that this is as easy as can be. Let's try one, shall we? Okay, we have let's say a 3 kilogram mass that has 50 joules of kinetic energy. Sounds good. A 3 kilogram mass has 50 joules of Ke. Well, I know it's mass. The only other question I could say is, what is its velocity? I have to make the question at least a little challenging, so what are the givens here? Givens, mass equals 3 kilograms. The energy, the kinetic energy, equals 50 joules, and I'm looking for the velocity. And you see, this is just amazingly easy. As long as you remember, where's the likely problem here? Let's get to it. The formula, it should put a red flag out. You know when there is something you need to pay attention to. Ke equals 1/2 mv squared. What do we have to pay attention to here? Because it's a place for mistakes to be made commonly. The square, right? So let's see how we solve this then. So I need to get velocity all by itself. So how do I do that? Well, 2 Ke gets rid of the 1/2 over m. That's equal to v squared. How do I get rid of that square here? Take the square root of both sides. So S and S, substitution and solution. V, I've taken the square root of it, so now I have V equals square root of 2 times the kinetic energy divided by the mass. Substituting in square root of 2 times 50 joules divided by 3 kilograms. Okay, that doesn't look so hard. All right, so 100 divided by 3, you know how this comes out, 33.3. Am I done? Am I done? Let's look at the units. A joule is a kilogram meter squared per second squared. I've divided that by a kilogram, killing off the kilograms. So I have meters squared per second squared. Do you see that? Do you see that down there? I have meters squared per second squared. I don't want that. Velocity's meters per second. So what did I forget to do? Hit that square root. Ah, now I've got it. So that would equal then, after I take the square root, 5.8 meters per second. 5.8 meters per second. So very simple formulas. Potential energy is even simpler. Important part, there's a square in it, so pay attention to that. Don't forget about taking the square into account. All right? That's kinetic and potential energy. We use them all over the place. The important part is the conversion of it, converting one to another. Now remember, potential energy does not just have to work against gravity. Potential energy is the work stored in it. Imagine if I'm pulling back on a bow and arrow. Well, when the bow is there, right, and I'm pulling back on the string, I've notched my arrow in, and I'm pulling back on the string, aren't I applying a force in newtons? And aren't I applying that over a distance in meters? Well, I am. Wouldn't that then be potential energy stored in that bow and arrow? Of course, that's exactly right. So I pull that back, and when I let it go, what does that potential energy immediately turn into? That potential energy immediately turns into kinetic energy. Oh, what fun. Thanks for watching.